Section 2.5 is on proof by contradiction. Now, this is a proof technique that you might want to use when your other proof techniques have failed, for direct proof or contrapositive proof or proof by cases. So here's the general idea behind a proof by contradiction. Now, we learned in Unit 1 that to negate a conditional statement of the form P implies Q, you end up with keeping the hypothesis, changing the arrow to an and negating the conclusion. So P and not Q. Right? We also know that if an implication is true, its negation must be false and vice versa. All right? And so sometimes it's easier to show that the negation of a statement, that P and not Q, is false, which would then imply that the original statement P implies Q has to be true. So the idea behind a proof by contradiction is to prove that P implies Q in a proof by contradiction, we assume the negation. We assume P and not Q. And then we find some sort of a logical contradiction to either an assumption or a known fact, which would then show that the negation, P and not Q, is false. So if you can find a contradiction to the negation statement, P and not Q, then you'll be able to conclude that the original statement is true. All right, now notice that it doesn't have to be an implication in order to use proof by contradiction. You can still use proof by contradiction as follows. If your statement is just some statement of the form P, then to prove it by contradiction, assume not P, assume the negation of P, and find a contradiction. If you find a contradiction, that would mean that the negation of P is false, and therefore your original statement P is true. But for the most part, we'll be looking at statements of the form P implies Q. All right, let's look at an example. Suppose n is an integer. If 7n minus 5 is even, then n is odd. Now, you could prove this, well, directly would be hard, but you could certainly prove this by contrapositive. But we're going to practice by using proof by contradiction just to understand how this works. So this is a statement of the form P implies Q. So to prove this by contradiction, we're going to say, well, first of all, write our original assumption. Let n be an integer. Now we'll say, assume by way of contradiction P and not Q. So that 7n minus 5 is even, right? Leave the hypothesis alone. And that this is not true, not Q. So n is not odd, so n is even. So we're assuming and hoping to find a contradiction that P and not Q is correct. If we can find a contradiction, then we know that P and not Q, we know that the negation is false, so the original statement must be true. All right, so let's look for some sort of a contradiction here. We know n's an integer, and now we're assuming that 7n minus 5 is even and n is even. So by the definition of even, n is equal to 2k for some integer k. Well, then we would have that 7n minus 5 is really just 7 times 2k minus 5. Or 14k minus 5. All right, I haven't reached a contradiction yet. Nothing here looks like a contradiction. What might we find a contradiction in, though? So, we could either find a contradiction that n's an integer by somehow showing n's not an integer, or we can show 7n minus 5 is even as a contradiction. So if we can show that 7n minus 5 is actually odd, that will be a contradiction of our assumption that is even. So can we express this as an odd integer? So 2 times an integer plus 1 or minus 1? And in fact, we can, because I could rewrite this, for instance, as 14k minus 6 plus 1. Because negative 6 plus 1 gives you negative 5, so I've just rewritten that negative 5 so that I have a plus 1 at the end. And now I can factor a 2 out of these first two terms to get 2 times 7k minus 3 with a plus 1 at the end. Now k is an integer, so since k is an integer, 7k minus 3 is an integer also. And so by the definition of odd, we've now expressed 7n minus 5 as 2 times 7k minus 3 plus 1 as 2 times an integer plus 1. So 7n minus 5 is odd. Why is that a problem? Because at the beginning we assumed it was even. A number can't be even and odd. Why? Well, okay, maybe we'll prove that in the future. But a number can't be even and odd. I think we can agree to that for now. So this is a contradiction because we assumed 7n minus 5 is even. Once you reach that contradiction, this proof is over. There's no way that these two things could both be true, which means the negation of this original statement is false, and so the original statement itself must be true. Therefore, if 7n minus 5 is even, then n must be odd, which is what we were trying to prove. Now, this would probably have been a cleaner proof if you just proved the contrapositive. Assume n is even, prove 7n minus 5 is odd. That's essentially all the work we did here, and so by doing this by contradiction, we sort of added an extra step of framing it in one way and then finding a contradiction later. But you don't always know from the get-go whether it would make more sense to use proof by contradiction or proof by contrapositive. So contrapositive is usually a first thing to try, and then you can try proof by contradiction if that doesn't work. Let's do another example. Let x be a non-zero real number. If x plus 1 over x is less than 2, then x is negative. All right. This might look familiar. We saw this inequality before in the vacuous and trivial proof section. We're going to try to prove this using proof by contradiction. All right, so let x be a real number with x not equal to 0. That's our assumption that x is a non-zero real number. And we'll prove this by contradiction. So we say assume by way of contradiction that the hypothesis is true that x plus 1 over x is less than 2, and that the conclusion is false, that x is not less than 0, which means x has to be greater than or equal to 0. Actually, it means x has to be strictly greater than 0, since we had assumed at the beginning that x is not equal to 0. So we're assuming by way of contradiction that x plus 1 over x is less than 2, and that x is positive, and we're going to find some kind of a contradiction here. How do we do that? Well, how does it help us to know that x is greater than 0? If we know x is positive, then that means I can multiply both sides of this inequality by x, and I can leave the inequality symbol alone. Right, so since x is positive, I can multiply both sides of the inequality without flipping the sign. If we didn't know whether x was positive or negative, then we couldn't really do that because we don't know if we have to flip the sign or not. Right, so we get x plus 1 over x is less than 2, and we multiply both sides by x. And distributing that through, we end up with x squared plus x over x, or just 1, is less than 2x. We're looking for a contradiction here, so maybe let's try moving 2x to the other side of the equation so that we have a 0 on one side. This would give us x squared minus 2x plus 1. Okay, let's try to factor this then. We'd have x, they need to multiply to positive 1 and add up to negative 2, so this would be x minus 1, x minus 1, which means we have x minus 1 squared is less than 0. Now, why is this a contradiction? Well, no number when squared can be less than 0. right? X minus 1 is a real number. And no real number, when squared, is negative. So this is our contradiction. There's no possible way that both of these statements can be true. If they were both true, you would end up having that x minus 1 squared is negative, and I know that that's impossible. Any real number squared should be greater than or equal to 0. So since we found our contradiction, this means that if x plus 1 over x is less than 2, then x must be less than 0. Right? So we're done with our second proof. Couple more examples. I forgot to leave myself space for this first one. So often statements that sound negative are good candidates for proof by contradiction. So I'm going to do this example here. Proof by contradiction that there's no integer that's both even and odd. All right, it seems like this shouldn't be true. There can't really be a number that's even and odd at the same time, but how do we prove it? Let's see. We have suppose by way of contradiction that the negation of this is true, that there is an integer that's both even and odd, that there is an integer x which is both even and odd. We're going to find some kind of a contradiction to a known fact here. By the definition of even, this means we can express x as 2k for some integer k. And by the definition of odd, this means we can express x as 2j plus 1 for some integer j. This already seems like this shouldn't make sense, but why? Let's go through the details. All right. Since x has to be equal to itself, that means we can conclude that 2k is equal to 2j plus 1. All right, why is that a problem? Maybe we can try to move 2j to the other side of the equation. All right. And so, factoring out a 2 gives us that 2 times k minus j is equal to 1. And dividing both sides by 2 gives me that k minus j is equal to 1/2. Here's the problem. If k and j are both integers, then k minus j must be an integer as well. But we've just shown that k minus j is equal to 1/2. Since k minus j, since k and j are integers, k minus j is an integer also. This is a contradiction because we showed that k minus j is equal to 1/2. So since we found a contradiction, we conclude that our original assumption is impossible, that there cannot be an integer that's both even and odd. Conclude that no integer x is both even and odd. Okay, cool. We'll do one more example together. Example 4, let a, b, and c be natural numbers. Prove that the only consecutive means 3 numbers right in a row, the only consecutive values for a, b, and c that satisfy the Pythagorean identity, a squared plus b squared equals c squared, are the integers 3, 4, 5. So this is saying the only Pythagorean triple that has 3 numbers right in a row are 3, 4, and 5. Let's try to prove this by contradiction. All right, so let's assume by way of contradiction that we have a, b, and c are natural numbers such that a squared plus b squared equals c squared, and it is not the case that a equals 3, b equals 4, c equals 5. This is not the case. oh, I also need to note consecutive, right? This is the important part here, that these are the only consecutive A, B, and C values that satisfy this equation. Consecutive means right in a row, like 3, 4, 5, or 7, 8, 9, or 12, 13, 14. All right, so we're going to try to find some kind of a contradiction here. Now, we're going to need to use the fact that these numbers are consecutive. So since A, B, and C are consecutive, that means we have some number A, we'll assume A is the smallest. We have that B is going to have to be 1 more than A, and that C is going to have to be 1 more than B, or 2 more than A. That's what it means for these three numbers to be consecutive. They come right in a row. A plus 1, A plus 2. So then we would have, since A squared plus B squared equals C squared, I could rewrite this, replacing B with A plus 1, A plus 1, and replacing C with A plus 2. All right, so let's go ahead and try to multiply these out then. We'll have A squared plus, my pen's running out. If I distribute A plus 1 squared, I'll get A squared plus 2A plus 1. It's running out too. And if I distribute on the right-hand side, I'll get A squared plus 4A plus 4. Where's the contradiction here? I don't see a contradiction yet. So let's try manipulating this a little bit. I'm going to move everything to the left-hand side of the equation by subtracting A squared on both sides. That'll cancel out these two. Subtracting 4A on both sides, and subtracting 4 on both sides. That's going to leave me with 0 on the right-hand side, and on the left-hand side I'll have A squared minus 2A minus 3. All right, so where's the contradiction? I don't see one yet. Well, we could factor. This would factor to, gotta multiply to -3 and add up to -2, so A minus 3 and A plus 1 would work, which means that either A minus 3 is equal to 0 or A plus 1 is equal to 0. All right, what's the problem here? Well, we already said that A is not equal to 3, so we can go ahead and throw out this first solution. But A can't be equal to 1, -1, because we started off by assuming A, B, and C are all natural numbers. So this is a contradiction. Because we assumed that A was a natural number, and A can't be equal to -1. Natural numbers are not negative, right? So that means, since our original assumption must be incorrect, we conclude that if A squared plus B squared equals C squared for consecutive natural numbers, A, B, and C, then it must be the case that A is 3, B is 4, and C is 5. Okay, so we've seen a few examples and we'll do some more practice ones in class. In the next video, we're going to spend some time looking at some of the more classic proof by contradictions that any math major should know.